Okay, so today let's continue the design of distillation column. Till now we have learned how to find the operating line of rectifying section. Now in distillation column you will see that feed enters the column at a certain stage. So what might happen in feed that based on the temperature and pressure of feed, it will contain some amount of liquid and some amount of vapor. Hence, based on the quality of feed, which we represent by the quality of feed represent by the Q, it said what amount of liquid the feed contain and what is the amount of vapor that the feed contain. Based on that, the liquid go into the stripping section part and the vapor is go to the rectification section part. So feed conditions, if you consider like if feed at a bubble point and is a saturated liquid, the Q will be 1, and if feed at a dew point saturated vapor, Q will be 0. uh, Feed is a mixture of uh, any liquid and feed will be the mixture of liquid and vapor, so Q generally represent the fraction of feed that is liquid. So it is the feed uh, liquid amount divided by the total feed amount. So now you can imagine feed will always be like this. So now you can see if I had only the liquid it will become 1, if I only had the vapor it will become 0. These two values you can determine. So this is how we define the feed quality in case of distillation operations. Now based on the feed quality, what will happen, the mole fraction of the component in the feed, that is XF. Let's say XF will rise somewhere here. You directly draw a line to goes to the 45-degree line. From there we need to find the Q line which define where my feed will lie on the operating lines. So another this is the one way I say the Q value generally calculated in the HAV minus H feed, HV minus HL, where H represent the enthalpy, and HF is the enthalpy of feed, and HV is the enthalpy of liquid, and HL is the vapor, and HV is the enthalpy of liquid. So this is how you calculate the feed. Now let's also determine the operating line of the feed section. Feed section operating line, because we also need to figure out where our feed section will lie on the curve so that we can find where it is going to intersect with the line of the top section, that is the rectifying section, feed section operating line. So on the feed tray you might consider that the some fraction of the feed will, let's say what will happen at feed tray. Here it is feed that is coming from top, some liquid will be coming from bottom, some vapor will be coming, and some liquid will be leaving it, which will be the LF, some vapor will be leaving it and some liquid will be leaving it. It will be VF minus 1, that vapor is coming, and it will be L, F plus 1, that liquid is coming. So if I say at a feed tray, what will basically happen, the mass balance, if I do the amount of liquid that is coming plus amount of liquid that is added by feed, that is basically QF is equal to the amount of liquid that is leaving. Similarly, the amount of vapor that is leaving is equal to amount of vapor that is coming plus 1 minus Q, the amount into the feed flow rate F, the amount of vapor that is leaving. So these two are the equations. And for the component balance of the most volatile component, that is the component 1, if I do it in the rectification section, which is the above the feed tray rectification section and stripping section, if I do the balances, so how they will look like: V into Y is equal to L into X plus T into XD for this section considering feed in. Similarly, V dash into Y equal to L dash into X minus BXB considering the bottom product, considering the distillate feed and the tray at which feed is entering. So once you did that, you will figure out V minus V dash into Y is equal to L minus L dash into X plus D XD plus B XB, which make more sense. So what is L dash and V is here. So let me draw the diagram. I think I might have confused you by using the different notation. So you can see this I consider DXD, this is BXB, this is the feed F, XF is the feed, Q into XF, Q into F is liquid, and Q in 1 minus Q into F is vapor, and F is the total feed rate. At this rate is entering, liquid leaving is LX, X dash, vapor coming is V dash, Y dash, vapor coming down is the XL, vapor going above is the YV, where Y is the mole fraction of the most volatile component. So after arranging these two, uh, you can also now what will I do? I will make the balance on the entire column. So entire column feed is coming F into XF, and the amount that is going down of the most volatile component is BXB and BXD. So this is the overall mass balance. Now substituting L dash minus L, V dash minus Y. So now what I will do, I will gonna substituting these things. So here if you focus, Y will be from the top equation, Y will be L minus L dash, L minus L dash by V minus V dash, sorry, V minus V dash X plus DXD BXB, DXD BXB, DXD and BXB, this you can clearly see is equal to F into XF, F into XF. L minus L dash, V minus V dash, you know what it is. If you look it closely, L minus L dash, what is the difference in L minus L dash? So it will also be V minus V dash. this is how it can be arranged. Now if you look carefully, L minus L dash. What is L minus L dash? L is the liquid that is coming, L dash is the liquid that is going. So L dash will be we clearly written it over. L dash, which is this, that is leaving the feed section, is equal to Q. So L dash minus L rearranging is equal to QF. So it can be replaced by QF, and V minus V, that vapor that is leaving, is equal to 1 minus Q into F. So after substituting this, it will become QF into X divided by 1 minus Q into F plus F into XF divided by 1 minus Q into F. Now you will see Y is equal to QX divided by 1 minus Q plus XF divided by 1 minus Q into F. So now from here you can understand this line, when X equal to XF, Y will be equal to Y will be equal to Q plus 1 minus Q XF. So when X equal to XF, Y is lie on this line. And the slope of this line will be minus Q upon 1. The slope of this line will be wait a second, sorry, I have done a substitution error. So it is initially V minus V dash, L minus L dash. So V minus V dash, we are substituting it from V minus V dash, and V is the amount of vapor that is leaving, which will be V equal to V dash plus 1 minus Q F. 1 minus QF. Okay. And I have substituted Y from yes, so only wrong thing I have done is, you see, L dash is the liquid that is leaving, so it will be minus QF. So L dash is the liquid that is leaving, L is coming, L dash is leaving, F is adding, so F is adding L plus FQ equal to L dash. So you can see L minus L dash is minus FQ. So I have done the substitution error, sorry for that. So it will be the minus sign, and hence once X equal to XF, you will have 1 minus Q divided by 1 minus Q XF. So it has a 1 point on the line Y equal to X, because here Y become XF, YF become XF. So it have one intercept on the 45-degree line. We got it. It has a one intercept on the, and it is a line which is Y equal to minus, I can say the operating line for the feed tray is 1 minus Q into X plus 1 divided by 1 minus Q into XF. So this will have some operation to do with this line. So now what will happen, if you have a saturated liquid where Q equal to 1, you can see the line will have an infinite slope and line will look like this. And if you had a saturated vapor Q, in case of saturated vapor, Q equal to 0, where we will in case of saturated vapor also, you have a Q equal to 1. In that scenario also, we will have a horizontal line. Here saturated vapor, this is saturated liquid, and in where some between you have a line. If we have a vapor q is less than 0 to 1 vapor liquid mixture, which is generally the case. So now to solve the, so now we have figured out these two things. What left to solve is like, let me draw it again. So let's say till now what we have done, let me summarize it. We have the vapor liquid diagram for the mixture. Now what we initially, I initially figure it out the operation line of the rectification section. So that line gives us the xd point. From this point there is a line that is passing, and I know about the feed thing. I will make it as a xf, and from there I figure out the line of the feeding section. So these two line we have figured it out. Now our next step is to design a distillation column, which is what means the design of the distillation column. First, to find out R minimum number of stages, operating R, duty of column, where R is the reflux ratio, duty of column, and many other things. So how we are gonna find it? So let me first write the every equation for you. So ROL, rectification section operating line, is y equal to R divided by R plus 1 xd, sorry, not xd, x plus 1 upon R plus 1 xd. Okay. Next I had y operating line, feed operating line, y equal to, we have just determined this line, y equal to minus q 1 minus q x plus 1 upon 1 minus q xf. Now the other information that is given to us is the diagram, equilibrium diagram. I am drawing the equilibrium diagram. So this is my y equal to x line. This is the vapor liquid equilibrium chart. Now what the points you know? First of all, you will know the xf. You will also know the desired xd you want, and you also know the xb, bottom product. Both you draw straight lines, make them here. Now as feed is constant, or what means by feed is constant means like property of feed is constant. So its property is constant, hence what will happen, you have your feed, xf will be here. From this point there is a line passing at a slope of minus q, 1 minus xq, somewhere like between this. I am assuming q is between 0 to 1. Now what will happen, this line which will pass from xd and yd, where yd is equal to xd, this point it has a slope of r plus 1. So based on the r, it might meet this line outside the equilibrium region. But what will happen when these two line, the operating line of the rectification section, meets the feed line outside the equilibrium section, at those value of R, distillation cannot be done. FOL outside equilibrium um, region or above equilibrium curve. Why is this so? Because after that there is no point you are gonna achieve it, because the max you can achieve. See what it means. It is saying there is a point where I can get this amount of uh, where I can get this amount of mole fraction of X in my mixture of the component 1 and the amount of, but the maximum we can go is till the equilibrium point where both come in equilibrium. You start heating the mixture, but you can't do this. You are fixing the amount of X in the mixture and then you cross such that you get more B compared to X in the mixture. You, because what will happen, you have this XB, and when you have this XB, you are fixing the XB, you start heating, the amount of X in the mixture will start going up. This line represent as you are heating, at every heating the mole fraction of the vapor will start changing. But what will happen, it is not gonna cross the equilibrium point. So for the point being, once for the value of R, XB, let me change the color. So the value of R at which ROL, this is ROL for R minimum, at which these two meet within the region first. So why this is called R minimum, because at this number of stages will be infinite. Let me explain you why. Because now what will you do, you will draw the number of stages from here. This is one stage, this is second stage, this is third stage, and then you go little bit, you zoom in, there is still a stage, there is still a stage, and so on. You will never able to cross the ROL and feed location to go on the stripping section side. So now how to find the stripping section operating line? First you can derive it the way we have derived it, or otherwise from the intersection point of these two, you just join the XB, that is your operating, that is the RO, sorry, that is SOL, stripping section operating line. So I hope you have clear with the concept of R minimum. Now what is the R, what is the concept of minimum number of states? So at minimum number of states, you see I know the XF, XL and everything. Now you imagine, as I just decreasing it, as my R is increasing, the slope of this line is going up, and going up, because the slope is R divided by R plus 1. As R become infinite, this line, when R is equal to infinite, the slope of this line is equal to 45 degree. Yes, the slope of the line will become 45 degree, and because R divided by R plus 1 will come 1, that is 10 10 45 degree. When R is less than infinite, yeah, R is some finite value, it is always less than 1, and on the curve of tan theta it is always less than 45 degrees centigrade. So you might have a 0 degree curve, straight curve, then you are making it little bit close to this line. So what will happen at R minimum, how we decide the minimum number of stages? Let's say you use the infinite reflux ratio. So what will happen, this line will merge with the r equal to 45-degree line. Are you with me? Assume you make the r equal to infinite number of, you are doing the reflux ratio as infinite. Whatever is coming in, you are just directly putting it in the column. So at, if you are refining it again and again and again, then what will happen? You don't require much number of states. So this is my xd, this is my xf, and this is my xb. Now you imagine x y equal to r upon r plus 1 xd plus x plus x divided by xd r plus 1. Now you imagine when r equal to infinite, what will happen to this term? This will xd r plus 1 will equal to 0, r equal to infinite, x is equal to r plus 1 equal to r plus 1, r divided by r plus 1. This is slope of line, it will become 1. So line will coincide with y equal to x. So this is my this will be my operating line when r equal to infinite, and this is my operating line of the rectification section. Similarly, the operating line of the stripping section will be this, which is SOL. Now what will happen? Now you draw number of stages. So first horizontal line. So in this scenario there are 3 stages required. The scenario I have drawn on my screen. So the 3 stages required. So now till now we have figured it out. And minimum is 3 at r infinite. So minimum number of stages occur at r infinite. R minimum, suppose for this to have, I assume that r is equal to 3, and with some graph given to me, r is equal to 0.2, I achieved it, that the intersection of ROL and FOL lie within the equilibrium region. First come in the equilibrium, not lie. First time they touch, when they come from the above, the first time they touch here, uh, or at the edges, or they touch at the equilibrium curve, that r I named as the r minimum, and for me it is 0.2. That can be calculated if you have the real case scenario. If you real case scenario means you also have the data in numbers and you are ready with chart paper. So it will, I will make it as r minimum equal to 0.2. So you guys might know how we calculate it normally, how we calculated it normally, how to calculate it. You always don't do the chart papers. So what you will do, y equal to x, this equation, what will you do? This is a mathematical problem. You know y as a f of x for equilibrium curve, and y equal to r plus 1 x plus xd divided by r plus 1, first and second curve. Find the value of r for the intersection of these two. Similarly, value of q, not q is fixed. So basically how you do it, very easy. I confused, sorry, I do the wrong way. You know the feed, that is y equal to minus q xf divided by 1 minus q plus xf divided by 1 minus q. So sorry, this is x, this is the operating line of operating line of the feeding section. So now you find the intersection point of these two, intersection of these two, that point will lie on the curve y equal to x divided by 1 plus r into r plus xt divided by 1 plus r. So the point x and y you put into this equation, the xi and yi into this equation, and find the r, that r is r minimum. So that's how you calculate this value. Now how we calculate the number of stages, or how we find out R operating. So R operating in general is R minimum into 1.5. In general we use this value, so for us it will become 1.5 into 0.2, which is 0.3. So now how I calculate number of stages at this operating reflux ratio? Again I will go to the chart. I will have XF, I will have XD, I will have XB, and what I want to do, I already know. So this will be my line of, I will say ROL. This will be my line of feed FOL, and based on these two intersection points, and knowing that these 2 points will lie on the stripping section operating line, this will be my SOL. Now what I will do, I will draw the number of stages. So this is my first, sorry, this is my first number of stages. Now what happened, this go there, and this is my second. So second stage is my feeding stage, because at this the feeding point is lying. Then I go third, then I go fourth. So there are 4 number of stages that are required, and I will have more, XB will be more refined. So in this case you are gonna required number of stages equal to 4, reflux ratio equal to 0.3. So this is the first design of your distillation column. Next we will learn how to find the distillation energy